Logarithmic equations, algebra 2 trigonometry regents. So I don't have any notes on this slide because we're just going to use the properties and the properties and conversions that we've learned in the previous two lessons. Most notably, the conversion property that's if you have, say, log a b equals c, that in exponential form is a raised to the c equals b. So that would be a to the c equals b. And so a lot of these logs, what we're going to do is we're going to basically convert it into exponential and then solve something a little bit more familiar. And you may see some of the properties from the previous lesson, like say log a plus log b. It can be written as a single log as the product ab. So you'll see some of that too. But first, this example number 1, find the value of x. This is a single log base 3 of x minus 2 equals 2. And when you have a single log equals a number, you're going to just do a simple conversion into exponential form. So that's this raised to this equals this. So that is 3 to the second equals x minus 2. And we did some basic ones like this when we did our log properties. So you are familiar with this. 3 squared is 9 equals x minus 2. Add 2, and you get 11 equals x. And then you could, of course, substitute it in there to check. The one thing you have to remember about log equations is that if x is ever the base must be greater than 0. So a log base must be greater than 0. So it's kind of like those radical equations where sometimes we got two answers for the radical equation and we rejected one of them because a square root can equal a negative. Well, it's just like that. So just keep that in mind, that a log base must be greater than 0. It cannot equal 0, and it can't be negative. So if x is ever the base, you have to check your answers out and make sure you don't reject one or two. So solve algebraically. Again, I have a single log equal to a number, so I'm going to do a simple conversion. This raised to this equals this. So that is 27 to the 4 thirds equals 2x minus 1. And I can simplify 27 to the 4 thirds. That can be done with a calculator, fine, but we don't need it. The bottom means cubed root, so it's like the cubed root of 27, which is 3, and that to the 4th power, and I know that 3 to the 4th equals 81. So 81 equals 2x minus 1. And then simply add 1 to it. We're looking at 82 equals 2x, and dividing x equals 41. Again, you can substitute that in there. I'm not too concerned with the checking when the base isn't the variable. Like I said, that's the one time where that could get a little tricky. All right, one more equation here, one more example. And what we see here is that there's two logarithms. There's a double log equal to a number. And so when I have a single log, like in these previous examples, I just did a conversion. But when I have a double log, I'm going to need to use a property to get it to be a single log so I can convert to exponential. So the property that we have here is a logarithm, base 9, plus another logarithm, base 9. And they have to be the same base in order to use these properties. That's why sometimes we saw the little b's. So they have the same base, so that means I could write it as a single log with that common base of 9. So you do nothing with the base. You don't add or multiply the bases. You write it as a single base. It's almost like when you have a common denominator of fractions and you add them together, you still have that same denominator, just add the top. Well, the common base logarithms being added, what we do is, let me go back to my first slide, is that when you have a common base being added, you write it as a single log with a multiplication property happening. So what I'm going to do is write this as a single log base 9 by multiplying half and x. So these get multiplied. So that is a half times x. So 1/2 x. And I could write that as a half x, or I could write it as x over 2. Either way, same thing. And that equals still 3 over 2. So if you have a log equation that has multiple logs with a common base, you can use the properties Plus means multiply. If there's a minus between them, I would do half divided by x. An exponent raised by an exponent can go on the front. Those properties we did in the previous lecture would be helpful here. And so now that I have a single logarithm, this raised to this equals this. And so that is 9 raised to the 3/2 equals half x. And I can simplify 9 to the 3/2. That is the square root of 9, which is 3, and 3 cubed is 27. So I'm looking at 27 equals half of x. And I want to get rid of this half x, so I'm going to divide by half. And dividing by half, 27 divided by half, is the same thing as actually multiplying it by 2. So x equals 54. And the reason why 27 divided by half, the reason why it's the same thing as multiplying by 2 is because remember, dividing by a fraction, you could also write it as timesing the reciprocal of the fraction times 2 over 1. And so that's why we end up with 54. And again, that since my x is not my base, I'm not too concerned to check it out, but it does work out. And you can certainly check it, and it will work out just fine. Okay, so that's basically it for log equations. You want to, when it's a single log equals a number, just convert its exponential and solve. When it's a multiple log, you're going to have to use a little log properties to get a single log, which then you can convert to exponential and solve from there.